Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is Shimshad Ali, Partner Technology, Sarad University. Today we are going to learn about the slope stability analysis, or you may say in another word, the analysis of slope stability. What are the main methods used for the analysis of the stability of the slopes? This is our week 13 or lecture 13, 5th semester, BSc Civil Engineering Technology. You can access this lecture at portal.su.edu.pk. So let's begin our today's lecture. First of all, the introduction. The quantitative determination of the stability of the slope is necessary in a number of engineering activities such as the design of dams and embankments, analysis of stability of natural slopes, analysis of stability of excavated slope or engineering slopes, analysis of deep-seated failure of foundation and retaining walls. Quite a number of techniques are available for these analyses, and in this chapter, the more widely used techniques are discussed. Extensive reviews of stability analysis have been provided by Chaudhary 1978 and by Schuster and Grizik in 1978. In order to provide some basic understanding of the nature of the calculations involved in the slope stability analysis, the case of stability of infinitely long slope is initially introduced. The factor of safety. The factor of safety in other engineering design and other engineering structure is somewhat different from the factor of safety of the stability of the slopes. The factor of safety is commonly thought of as the ratio of the maximum load or stresses that a soil can sustain to the actual load or stress that is applied. Referring to figure number 11.11. This is basically the figure 11.11. Definition diagram for factor of safety. Here we have the normal stress. Here we have the shear stress. This is the cohesion. This is the failure envelope of soil. Just like this diagram is being developed from the Mohr-Coulomb failure envelope. This is the angle of internal friction. This is basically the tau FF, and here we have the tau. This is the normal stress. So, the factor of safety F with respect to strain may be expressed as follows. Here we have the F is equal to tau into FF divided by the tau, where tau into FF is the maximum shear stress that the soil can sustain at the value of normal stress of normal, then and tau is the actual shear stress applied to the soil. This is basically the factor of safety. Two other factors of safety which are occasionally used are the factor of safety with respect to cohesion, FC, and the factor of safety with respect to friction. The factor of safety with respect to cohesion may be defined as the ratio between the actual cohesion and the cohesion required for stability when the fractional component of strength is fully mobilized. This may be expressed as follows. Tau is equal to C divided by the FC plus normal stress tangent into theta. The factor of safety with respect to friction may be defined as the ratio of the tangent of the angle of shearing resistance of the soil to the tangent of the mobilized angle of shearing resistance of the soil when the cohesive component of the strength is fully mobilized. One way in which this may be expressed is as follows. Tau is equal to C plus normal stress into tangent theta divided by F of the tangent theta. This is basically the factor of safety for the cohesion and for the friction. CULMANN method. Now we are going to only discuss. Remember that we are going to discuss just the methods which are used for the analysis of the slope stability. A technique for the calculation of the slope stability based upon the assumption of a plane surface of failure through the toe of the slope has been proposed by CULMANN, C. Taylor, 1948, in figure 11.2. The line QS represents a plane potential failure surface. Surface. The force acting on the wedge QRS are indicated on the figure as the weight of the wedge W, the mobilized cohesive forces Cm, and the mobilized frictional force P into theta into n as the mobilized angle of shearing resistance. These three forces are placed in equilibrium to yield the following expression. Basically, the CULMANN method is the method of the equilibrium. When these three terms are in equilibrium, so we can express the mathematical form of the, this is that the C into M mean the mobilized cohesive force divided by P into G into H is equal to cos of the I plus theta into M minus 2 theta minus cos I minus theta M divided by 4 into cos theta M into sin I. Okay, the theta is equal to the angle of internal friction 0 method of the slope stability analysis. This method is used for the soil or the cohesive soil basically. Since the surface of sliding for many slope failures have been observed to follow approximately the arc of a circle, most of the common used analytical techniques for calculation of slope stability involve the assumption of a circular failure arc. Most of the techniques discussed in this chapter are based upon this assumption. For composite failure surfaces, analysis has been developed by Morgenstern and Price in 1965 and by John Boo in 1973. The problem is stated in the upper part of the figure 11.3. The forces acting on the sliding wedge of soil are the weight W, normal stresses A which act along the failure surface, and resisting shear says tau which also act along the failure surface. The factor of safety F may be defined for this situation as follows. Ordinary method of slices. Most commonly used method is the ordinary method of the slices. Other one may also be used, but in literature, as I have learned, that the slice method is used most commonly. In cases where the effective angle of shearing resistance is not constant over the failure surface, such as in zone of dams where the failure surface might pass through several different materials, the fraction circle method cannot be used. A slice method is more appropriate in this situation. With the method of slices, the sliding wedge PQS is shown in the figure 11.5 is subdivided. As you can see, this is basically the slice. Plus mean a piece which will be analyzed. This is the delta into x, this is a w, this is the x into n, this is the e into n, and this is also the shear and illustration of ordinary method of the slice. Bishop method of slices. A slice method of slope stability analysis which involve a different procedure and give different answer compared with the ordinary method of slices has been proposed by Bishop in 1955. With this method, the analysis is carried out in terms of stresses instead of forces, which were used with the ordinary method of slices. The stresses and forces which act on a typical slice and which are taken into account in the analysis are shown in figure 11.8. The major difference between the Bishop method and the ordinary method of slices is that resolution of forces take place. Basically. This is basically the Bishop method of the slices. Short-term and long-term stability. This is the most important part of today's lecture. In carrying our slope stability analysis for design purposes, it is wise to check both short-term and long-term condition. When you are going to analyze the stability of the slope, so you probably and you must have to check it for the short-term as well as for the long-term condition as well. For the short-term condition, an effective stress analysis could be used, but this will require an estimate of the pore pressure that will be developed. These are the main points. That for the short-term condition, effective stress analysis, the pore water pressure will be estimated. Alternatively, a total stress analysis could be used, but this will only be applicable in cases where the pore pressure changes are entirely dependent upon the stress change. For long-term condition, an effective stress analysis is normally carried out since the pore pressure are used independent of stress change. For this analysis, estimates of the pore pressure, for example, by means of the flow nets, are required. In examining the stability of a foundation site for following embankment construction, the short-term case is often more critical than the long-term case. As discussed by Bishop and Brigham, 1960, this is illustrated in figure 11.10 with an examination of the stress change at a typical point P beneath the embankments. In this case, the pore pressure at point P at the end of the construction is determined largely by the stress change produced by the embankment. The pore pressure for a long-term case, on the other hand, is determined by groundwater condition. In this idealized example, the factor of safety is considered as the ratio between the soil strength and the applied shear stress. It is seen that in this case, the minimum factor of safety is obtained at the end of construction, that is, for short-term condition, as time elapses and the construction pore pressure dissipates, the factor of safety increase is illustrated in the sketch. On the other hand, figure 11.11 illustrates the stress changes at a typical point P beneath an excavated slope. Here, the pore pressure at the end of excavation are determined by the stress change produced by the process of excavation. The long-term pore pressure, as in the previous example, are determined by the groundwater condition. In this case, it is seen that the soil strength decreases with time and the factor of safety also decreases with time, which makes the long-term stability condition the critical one to be examined. This is the figure. This is basically the P. This is the excavation, applied shear stresses. This is the applied shear stresses. Pore pressure, and the pore pressure increases. Soil strength increase found in the factor of safety. Variation of factor of safety. The safety factor with the time for excavation of a slope for Bishop in 1960. So this is it for today's class. Hope you will learn something about the methods which is used for the analysis of the slope stability. And in next class, inshallah, we will learn about the structural design of foundation, combined and strip footing also. So thank you so much. If you have any query regarding today's lecture, then you will let me know at your portal.su.edu.pk. Take care.